Have you ever wondered about the magic that happens inside a camera? How does a round lens capture a rectangular photo? It's a question that highlights the fascinating interplay of physics and engineering that allows us to freeze moments in time. We peer through the circular portal of a lens, yet our images emerge as portals onto flat rectangles. This transformation from a curved reality to a flat representation is at the heart of photography. Light, in its natural state, travels in straight lines. A camera lens with its curved surface bends these light rays. This bending, known as refraction, is the key to focusing light onto the camera's sensor. Imagine a magnifying glass focusing sunlight to a single, intense point. A camera lens works similarly, gathering scattered light and directing it to create a sharp image. But the story doesn't end there. The magic truly unfolds when this focused light hits the camera's sensor. This digital canvas is where photons, the fundamental particles of light, are transformed into electrical signals. These signals are then processed and arranged to form the digital image we see. The journey from a round lens to a rectangular photo is a testament to human ingenuity. It's a process that seamlessly blends physics, engineering, and art. In the following sections, we'll delve deeper into this process, exploring the intricacies of lenses, sensors, and the captivating world of digital photography. A camera lens is more than just a piece of glass. It's a carefully crafted optical instrument designed to bend light in a precise way. The shape of the lens, along with the type of glass used, determines how light rays converge after passing through it. This convergence point is where the image is formed, sharp and ready to be captured. Think of a lens as a series of prisms arranged in a circle. Each prism bends incoming light rays towards the center of the lens. The curvature of the lens dictates how much the light bends. A more curved lens, like those found in wide-angle lenses, bends light more dramatically. A flatter lens, like those used for telephoto photography, bends light to a lesser degree. This interplay of curvature and refraction allows photographers to control the field of view. Wide-angle lenses capture a broader scene, perfect for landscapes or architecture. Telephoto lenses, on the other hand, magnify distant subjects, ideal for wildlife or sports photography. Understanding how a lens bends light is fundamental to understanding photography. It's the foundation upon which all other aspects of image creation are built. In the next section, we'll explore the different types of lenses and how they influence the final photograph. Just as a writer chooses words to craft a narrative, a photographer selects lenses to shape their visual story. Each type of lens offers a unique perspective, influencing not just the composition, but also the overall feel of an image. Wide-angle lenses, with their expansive view, are often used to emphasize the grandeur of a scene. Think of sweeping landscapes or towering cityscapes. These lenses can also create a sense of depth and immersion, drawing the viewer into the photograph. Telephoto lenses, on the other hand, excel at isolating subjects. They compress perspective, bringing distant objects closer and blurring the background. This effect is often used to create a sense of intimacy, or to highlight the subject's emotions. Between these two extremes lies a range of lenses, each with its own strengths and characteristics. Macro lenses allow photographers to capture the intricate details of tiny subjects. Portrait lenses are designed to flatter the human form, creating pleasing blurs and soft transitions. Choosing the right lens is an art form in itself. It's about understanding the story you want to tell, and selecting the lens that best complements your vision. The lens becomes an extension of the photographer's eye, shaping how we see and experience the world. While the lens focuses light, it's the camera's sensor that truly captures the image. This unassuming electronic component is the heart of digital photography, transforming photons into pixels that form our digital memories. Imagine a vast grid of light-sensitive cells, each one ready to absorb incoming photons. This grid is the sensor, and each cell acts like a miniature solar panel, converting light energy into electrical charge. The more light a cell receives, the stronger the electrical signal it generates. These signals are then amplified and processed by the camera's image processor, a tiny computer chip responsible for converting the raw data into a usable image file. The processor analyzes the brightness and color information from each cell, assembling them into the final photograph. The sensor's size and resolution play a crucial role in image quality. Larger sensors can capture more light, resulting in better low-light performance and a wider dynamic range. Higher resolution sensors, with their densely packed cells, produce images with more detail and sharpness. Section 5. The art of capturing light, sensors up close. The sensor's surface is a marvel of engineering, a testament to our ability to manipulate matter at the microscopic level. Each light-sensitive cell is meticulously crafted to maximize its light-gathering capabilities. These cells, often referred to as photosites, are typically made of silicon, a material known for its semiconducting properties. When a photon strikes a photosite, it knocks loose an electron, creating an electrical charge. The number of electrons released is directly proportional to the intensity of light hitting the photosite. To capture color information, each photosite is covered with a color filter. The most common arrangement is the Bayer filter, which uses a pattern of red, green, and blue filters. By analyzing the intensity of light passing through each filter, the camera can reconstruct the full color spectrum. The process of converting light into electrical signals is known as photoelectric effect, a phenomenon that revolutionized our understanding of light and laid the foundation for digital imaging. It's a testament to the power of scientific inquiry and its profound impact on our lives. Section 6. Pixels, painting the digital picture. The electrical signals generated by the sensor are not images in themselves. They are simply raw data, a digital representation of the light that fell upon the sensor. To create a viewable image, these signals must be organized and assigned color values. This is where pixels come in. Think of pixels as the building blocks of a digital image. Each pixel represents a single point in the image, characterized by its brightness and color. The number of pixels in an image determines its resolution. More pixels mean a sharper, more detailed image. During image processing, the electrical signals from the sensor are mapped onto a grid of pixels. Each pixel is assigned a color and brightness value based on the intensity of light detected by the corresponding photosite. This process, known as demosaicing, interpolates the color information from the Bayer filter to create a full-color image. The final step involves adjusting the image's contrast, sharpness, and color balance to create a visually pleasing result. These adjustments can be made automatically by the camera or manually by the photographer using image editing software. Section 7. From circle to square, the illusion of shape. We've explored how lenses focus light and sensors capture it, but the question remains, how do we get a rectangular image from a round lens? The answer lies in the way the image is cropped and projected. While the lens itself is round, the sensor is rectangular. This means that only a portion of the circular image projected by the lens is actually captured. The outer edges of the circle fall outside the sensor's boundaries and are therefore not recorded. Furthermore, the image projected by the lens is not flat, but slightly curved. This is due to the nature of light refraction and the shape of the lens. To create a rectangular image, the camera's software applies lens correction algorithms that digitally flatten the image, ensuring straight lines remain straight. The result is a rectangular image that accurately represents the scene captured by the lens, albeit with some creative cropping and digital manipulation. This process is seamless and happens automatically, allowing us to enjoy the illusion of a flat image from a curved reality. Beyond the lens, real-world applications. The principles of lenses and sensors extend far beyond the realm of photography. They form the backbone of countless technologies that shape our modern world, from medical imaging to space exploration. In medicine, cameras equipped with specialized lenses and sensors allow doctors to peer inside the human body without invasive procedures. Endoscopes, for example, use tiny cameras to examine internal organs, while X-ray machines capture images of bones and tissues. In astronomy, telescopes utilize massive lenses and highly sensitive sensors to capture light from distant stars and galaxies. These instruments allow us to study the cosmos and unravel the mysteries of the universe. Even our smartphones rely on the same fundamental principles of optics and digital imaging. The compact cameras in our pockets utilize tiny lenses and sensors to capture photos and videos, connecting us to the world in ways unimaginable just a few decades ago. The future of image capture advancements and innovations. The field of digital imaging is constantly evolving, driven by relentless innovation and a desire to capture the world around us in ever more detail and fidelity. New technologies are emerging that promise to revolutionize how we see and interact with images. Computational photography, for example, leverages the power of artificial intelligence to enhance image quality and create new photographic possibilities. By analyzing and processing vast amounts of visual data, AI algorithms can remove blur, improve low-light performance, and even generate realistic 3D models from 2D images. Sensor technology is also advancing rapidly. Researchers are developing new types of sensors that are more sensitive to light, have a wider dynamic range, and can capture a wider spectrum of colors. These advancements will lead to images with greater detail, richer colors, and improved low-light performance. The future of image capture is bright, with technology constantly pushing the boundaries of what's possible. As we continue to innovate and explore new frontiers, we can expect even more breathtaking images and groundbreaking applications that will shape our understanding of the world. Conclusion: the enduring allure of photography. From the earliest pinhole cameras to the sophisticated digital devices we use today, photography has always been about capturing light and transforming it into something tangible and enduring. It's a testament to human curiosity, ingenuity, and our innate desire to preserve moments in time. The journey from a round lens to a rectangular photo is a fascinating blend of physics, engineering, and art. It's a process that highlights the power of human innovation and our ability to harness the laws of nature to create something truly remarkable. As technology continues to advance, we can only imagine the incredible images we'll be able to capture in the future. But one thing remains certain: the allure of photography, the magic of freezing time and sharing our unique perspective with the world, will continue to captivate and inspire us for generations to come. References: Complete Guide to Photography, National Geographic. Retrieved June 1, 2024 from https://www.nationalgeographic.com/photography/. And Davies, J. How Cameras Work. Digital Photography School. Retrieved June 1, 2024 from https://digital-photography-school.com/how-cameras-work/.